In this series of Snap Circuits videos, we're looking at Project 354, Project 376. Project 354 is our transistor timer. That's how it looks in the book, and here it is on the board. And here it's similar to Project 342, where we're using a transistor and a capacitor coupled together to keep the relay here in an on state for a certain period of time. Now with our two transistor setup here, we've got our NPN connected with our PNP. Essentially, we've created our Darlington transistor setup, which we've seen in previous projects before. And so when we press our press switch, of course we got our slide switch here set to on. That's our master switch, and our relay, of course, drives our 6-volt light. So when we press the press switch, the relay comes on, and it also charges up our 10 microfarad capacitor there. And actually, I just realized that somehow I got this in reverse polarity. There. That's where I got it's supposed to be, even though it still works. But anyway, you press the press switch, the capacitor charges up, then feeds our two transistors, which then connects our relay contacts, causing our light to come on. Now, because we have a Darlington transistor setup here, it only needs a very tiny amount of current to keep this relay on here. As the capacitor discharges through our 10,000 ohm resistor through our transistors there, it will gradually get less and less to the point where this doesn't have enough power left, and our relay will close up, turning off our light. So within a couple more seconds here, we should be seeing that light turn off once that capacitor is fully discharged. Again, this proves the point of the Darlington transistors needing so little current for a contact like that to stay open. And now see that's turned off because our capacitor is completely discharged, and it takes roughly 45 seconds to a minute for that to happen. We can just easily restart it there. And again, it's running off our capacitor, discharging through our NPN transistor there. But again, because it has such high sensitivity across the transistor setup there, that it will stay on for 45 seconds to a full minute before that capacitor has too little charge to keep our light on. Just turn it off here. So that's how project number 354 works. Now we're going to move on to project 355, which is the light controlled relay. So here we are at project 355, the light controlled relay. There it is in the book, and here it is on the board. So here we get our usual 6-volt setup, although I'm using the power adapter with our S3 relay, which has its contacts being controlled via our NPN transistor that's being fed from our photoresistor. And we get a little additional limitation of 1,000 ohms with our 1K resistor there feeding our photoresistor. And then our output is controlled, again, via the relay to our 6-volt lamp. So when we turn the switch on, our lamp comes on because we have enough light coming down into our photoresistor there to provide enough current to our NPN transistor to trigger, thus connecting our contacts across our relay here, which allows our light to light up. Now, if we cover up our photoresistor, the light goes out because not enough light is entering the photoresistor now, and thus the NPN transistor cannot turn on there. Then the relay will not be able to connect. Now, of course, we let the light back in, light comes back on, cover it, the light goes off. And again, we're just changing the amount of current that's flowing to our NPN transistor there at its base via the photoresistor by how much light we're letting in. So again, the less light that comes in, the less current there is, so it's not going to be able to energize the contacts on our relay. If we let plenty of light in, well, now it's got enough current that it can do that. And thus our light turns on and off because of that. So that's how project 355 works. Now project 356 is the bulb alert relay. So what we do with that is we take our photoresistor away and put our 10K resistor in place here. Now, of course, if we do that, it stays on all the time, but what we do is we connect a point there between here, this little thing there. Anyway, the idea is that we're shorting to ground there, bypassing the NPN transistor. But when this link breaks, the light comes on, hence the bulb alert, because we have this connection here that's keeping it grounded, but once we take the ground away, like it's been broken somehow, the light comes on. So that's how project number 356 works. Now we're going to move on to project 357, the adjustable light control. So here we are with the adjustable light control. There it is in the book. Here it is on the board. And here we've got a similar setup using our photoresistor controlling our NPN resistor, which of course controls the contacts across our relay, which turns on and off our 6-volt lamp. Now this time we have our variable resistor on the base of the NPN, which is also of course getting the feed from our photoresistor. So by adjusting the resistance on our variable resistor, we can then adjust how much light is required to keep the contacts on our relay closed. So it's positioned all the way at the top. So it allows the most current from the photoresistor to come to the NPN transistor. Now if we start decreasing that, eventually we reach a point where the current is too low to power up our relay. Now if I take a strong enough light at this point, I still might be able to turn that on, as we can see. And once I take the flashlight away, there's still just enough current coming in to keep the contacts closed. Now if I cover it up, well now of course it turns off the contacts, but there's not enough current coming back in to close the contacts back up till I put a light back on there. So now it closes it up, and again I can bring it down more. Now if it's all the way down below halfway here, it doesn't matter how much light we put on it because we're only seeing this portion down here. We're not getting anything from up here anymore. So we have to push it up to get that. So that way we can control the amount of light required to close the contacts. So that is how project number 357 works. Now project 358 is the meter deflection. So here we are with project number 358, the meter deflection. There it is in the book, and here it is on the board. So here we're making use of our transformer, and our input is being fed via 3 volts, and we've got our 6-volt lamp here, which is both kind of used to limit the current, but it also gives us a visual indication of the energized state of the transformer, because that 6-volt lamp will glow when it's energized. On the output side of the transformer, we have our meter connected to the sender tap, and then on either side of the windings we have our D1 and D2 LEDs, and you see they're going in different directions based on their polarity. So we have one path that has current going this way, and this path has this current going this way. And the thing about a transformer, so I'll demonstrate here. So we press the button, watch the LED and the meter. Our red LED briefly flickers, and we also get a burst of motion on the meter there, showing the initial current bursted there. And we can see that our 6-volt lamp is illuminated because the field in our transformer is energized. Now if I release the press switch again, look at the meter and the green LED, you see our meter briefly went up a little bit again, and our green LED flashed because we got a burst of current that went in this direction. See, when we first turn on the transformer, we get a burst of current going in this direction, and when we take the current away from the transformer, we get a burst of current in the other direction. And this is how we get alternating current. By switching on and off our input signal on a transformer, we can generate an alternating current signal on the output. So that's why, if I did this fast enough, you can see our LEDs alternating back and forth there as I do this. And so that's how we get alternating current. you turn the transformer on and off, when the field becomes energized, you get a current in one direction. When that field collapses, when you take the power away, you get current in the other direction. So that is how project number 358 works. So we're going to move on to 359, which is AC to DC current. So here with project 359, the AC to DC current. There it is in the book, and here it is on the board. Essentially, it's similar to the last project, but this time we only have one diode, and we're using the full length of the transformer output windings instead of connecting off the center tap like we did before. So, like the name implies, it's AC to DC current because, as you saw before, we generate an AC current signal every time we press and release the button here. The catch here is that our diode is acting like a rectifier, and in the case of this, it acts as a half-wave rectifier. So when I energize the coils in the transformer, you see that the LED does not flash, so we get no meter deflection. But when I release the press switch, our light flashes, and we get some deflection on the meter from the burst of current from the field collapsing in the transformer, because our current goes this way. When, of course, when we energize the transformer, the current's trying to go this way, but the diode blocks it because the diode only allows current to go in that direction. So this is what we call half-wave rectification, because an AC signal goes like this, just like the 60 Hertz sine wave that we see on electricity here in the US. So with half-wave rectification, it's only seeing one portion. So it's either seeing only the top of the AC signal, or it's only seeing the bottom of the AC signal, but whichever one it's seeing, it changes it into DC, so we just get that pulse there. So that's how project number 359 works. So project 360 is the current meter. So here we are with project 360, the current meter. There it is in the book, and here it is on the board. And like before, we've got our meter set up on the max side of the transformer there with our regular diode instead of the LED and our 10,000 ohm resistor for limiting the current. So like before, this is a half-wave rectification, so it's having the power that we could get on the transformer there, but instead of the press switch and the light, we actually have our slide switch and our electric motor on this side of the transformer. So when we turn it on, the motor spins up, and you notice that we've got a continuous current reading on our meter there, right around 3 amps. And you can see it kind of fluctuate a little bit on the motor here, and I'll explain why that is. Kind of going from 3 to 4 milliamps. And that's because a motor like this uses brushes, so they got brushes around the part that's rotating, and as it rotates, those brushes are breaking contact, and by doing that, it interrupts the current flow. And as we've seen, when you turn on and off the current on this side of the transformer, then you induce an alternating current signal on the other side of the transformer, because you're energizing and collapsing the magnetic field, and of course that generates the AC signal. But because this is a half-wave rectifier, we get a continuous current reading, because if the diode wasn't here, this meter would not deflect at all, because the current is going back and forth like this on this side. Here it's just going in a loop like this, but again, remember, it's half-wave rectification with this single diode. So that's how project number 360 works. Now we're going to look at project 361, the buzzer, relay, and transformer. So here are project 361, the buzzer, relay, and transformer. There it is in the book, and here it is on the board. And like project 353, we have our relay set up in such a way that the coil is going to be able to turn on and off very rapidly, but we're also feeding its on and off actions to our transformer here, and then to our speaker. Now it usually has the C2 0.1 microfarad capacitor here, but you can take that away and put a simple 3 snap wire there to make the output a little bit louder on the speaker. Because if you look at how our transformer is positioned, we're actually stepping the voltage down. We're feeding the higher number of windings and then outputting on the lower set. So by doing that, the output actually steps down. So when this thing alternates back and forth, basically turning on and off, we of course induce an AC output signal through a transformer by energizing and collapsing the coil or winding inside, and then we hear that result through our speaker as a whine or a buzzing sound, again as this is switching on and off. So bring it to the speaker here, I'll turn it on for a little bit. So again, when power is applied, the coil on our relay rapidly switches on and off, so it's going pretty much like that really quick. And then of course that on and off signal is being fed to our transformer, which creates an AC signal that we can hear through our speaker. So that's how Project 361 works. So we're going to move on to Project 362, the buzzer and relay. So here we are with Project 362, the buzzer and relay. There it is in the book, and here it is on the board. And as opposed to the previous project, we don't have the transformer this time. Instead, we have the speaker and our capacitor connected directly to the coil of our relay. So like in a previous project where we had this similar setup with the relay buzzer, we have the contacts of the relay opening and closing very rapidly, which kind of makes a buzzing sound, but this time we're going to hear it also with the speaker as the capacitor charges and discharges with the opening and closing of the contacts. Now I'll do this for a short time because I don't want to make too much noise at this, but I'll try to bring the speaker up here so you can at least distinguish the speaker versus the relay. So again, the relay turns on and off very fast, creating a buzzing sound, but there's also a buzzing sound coming from the speaker. Again, it may be a little hard to distinguish with them so close together like in the project here. But again, as that capacitor charges and discharges with the opening and closing of the coil there, again it generates a wave, and then we can hear that from our speaker. So that's Project 362. 363, where we start working with our 7-segment LED again, with displaying the capital letter F. So here we are with our 7-segment LED, and we're going to run through Project 363 all the way to 376 with it. So we're starting with 363. It's going to have us display the capital letter F. So that, of course, we've got our circuit set up here with our 100 ohm resistor to limit the output, and we're not 3 volts. And of course we got our railing, so we connect our 2 snap wires across all the different points here to illuminate the different 7 segments of the display there. So again, we're making the letter F, so we're going to connect A. Well, actually, let me turn it off first. We have A first, and then we have E, and then F, throwing parts around, and G. So connect it like that, turn it on, and we print out the letter F because we're lighting up the 2 leftmost segments and the upper 2 middle segments. So that's 363, so let's do 364, displaying the letter H. So we're going to connect B, C, E, F, and G. So we got the connections like so, turn it on. Now we got the capital letter H, because we have the 2 left segments, the 2 right segments, and the center LED segment illuminated. Turn it off. So that's 364. Now we're moving to Project 365. We're displaying the capital letter P. So we connect A and P, E, F, and G. So we have the connections like so. Turn it on. And now we get the capital letter P because the 2 leftmost segments, the upper rightmost segment, and the upper 2 middle segments are illuminated. So that's project 365. Now we're going to move on to project 366. That's making the capital letter S. So we have A, F, G. A, F, G, C, and D. So we make the connections there. Turn it on. And now we get the capital letter S, which can also be interpreted as the number 5. Because we got all the middle segments illuminated, the upper left and the lower right segments illuminated. So that's project 366. Project 367 now has us displaying the capital letter U. So B, C, D, B, C, D, E, and F. So we have our connections like so. Turn it on. And we get the capital letter U, because we have the leftmost, the rightmost, and the lower middle segments illuminated. Turn that off. So that's project 367. Project 368 has us displaying the capital letter C. So we're going to connect A, D, E, and F. So all the segments on this side. Turn it on. And we get the capital letter C, because we have the top, bottom, middle segments and the 2 left segments illuminated. So that's project 368. Project 369 has us displaying capital letter E. So we're going to connect A, D, E, F, and G. So there's our connections. Turn it on. And we get the capital letter E, because we have the 2 leftmost segments and all the middle segments of the LED illuminated. So in fact, if you see E on something, that usually means there's some kind of error. If you see that on some kind of electronic device, especially an older one. Anyway, moving on to project 370, we have us display a period, or the decimal point, which is the DP. So we just connect the DP and turn it on, and we illuminate our little decimal point on the display. So that's all there is to 370. 371, we display a lowercase b. So we're going to connect C, D, E, F, and G. So there's our connections. Turn it on, and we get a lowercase b, because we have our 2 left segments, our 2 lowermost middle segments, and the right lower segment there illuminated. Turn it off. So that's project 371. Project 372 has displaying a lowercase c. So we're going to connect A, F, and G. There are the connections. Turn it on, and we get our lowercase c. Now, if we could also have this displayed down here, if we just move the appropriate connections down for it, but that's project 372, because we're showing the top middle, the middle, and the upper left one. But again, we can move this down to the bottom of the display if we so chose, just by moving the connections. So that's project 372. Project 373 has us displaying a lowercase d, so we connect B, C, D, E, and G. Our connections are like so. Turn it on, and we get a lowercase d. Basically, this is just a rotated version of Project 371 with the lowercase b, just because with the connections in different spots. So we have the two rightmost segments, the two lowermost middle segments, and the lower left segment illuminated. So that's Project 373. Project 374 has us displaying a lowercase e. So we're going to connect A, B, D, E, F, and G. So this connected like so. Turn it on. And it's not a lowercase. Well, actually, yes, it is a lowercase e. So I was going to get that wrong. So we got our two leftmost segments, all our middle segments, and our upper right segment illuminated. So that's Project 374. Project 375 has this displaying a lowercase h. So we connect F, E, G, and C. We turn it on, and we get our lowercase h, because we have the two left segments, the middle segment, and the lower right segment illuminated. Turn that off. And the last one, Project 376, has us displaying the letter O, or lowercase o. So we connect C, D, E, and G. Turn it on, and we get our lowercase o. And again, just like I was showing with 372 with the lowercase c, we could also have this on the top portion of the 7-segment LED display instead of down here, just by moving the connections up. So that is Project 376, and that concludes this set of Snap Circuits videos.